be recording.
Hello, hello. Okay, let's begin, everyone. I still have the Jackie. This is for you. Just a quick remark regarding problem 4.4. The logarithm that I mentioned in class already, even though written as log, but in math it means natural logarithm, okay? And it's written in two places. The first is here and the second is here. And also, in addition to having mentioned in class, you have the solution guide. When you do the computation, you can always check. If it doesn't work out, probably you did something wrong. And that's likely, this is one possibility that of mixing up between natural logarithm and log of base 10. Okay. Yeah, so I'd like to talk a little about section 9C to complete the example with the parabola that I started already, show the animation, and then after that I'd like to go to 4.7, okay, to talk about, this is setting up for the Beatles topic, detection of musical notes by using fast Fourier transform. Okay, so let's go to 9C, section 9C. So I bring up section 9C here. On the left window, I have already showed you this parabola, right? This is x to the power 2 here after completion, after making it into an even function over the period from -1 to 1. Okay, so let me, and on the right window, I just want to go down to where the computation of the Fourier series coefficients is, and then go to the middle window to zoom in. Okay, so for easy viewing, and so this is okay. So now regarding the plot, I don't think anyone would have any problem anymore. It's just a parabola. Now we have extended the parabola to the period, which is from -1 to 1, right? And so the period P, remember, is 2L, and in this case 2L would be equal to 2, so L equal to 1 in this example. Right? And I rewrite here as well. And you can note that, I already wrote here, P equal to 2L, and 2L is equal to 2 because the interval is from -1 to 1. So therefore L is equal to 1. Cap L is equal to 1. And if you use the formula that I have derived, omega is 2 pi over p, right? And p is 2, so you have 2 pi over 2. So the angular velocity, omega, or also called the circular frequency in vibration, is equal to pi. Okay. And now moving forward, because the function f of x, which is x squared, was even, so therefore all of the coefficients bn would be equal to 0. And so for active learning credit, let's see whether someone could remind the class the reason why the coefficients bn would be equal to 0. Okay, anyone? Remember, bn is the coefficient for sine function. Okay, so we have is that John and Paul. Okay, let's start with John.
The function you have to integrate for bn is even, so it's symmetrical across the y-axis. So anything that's under the graph on the negative side cancels out the positive side.
The function that you need to integrate for bn is even.
Yeah.
But why is bn 0?
Because
what is the formula for bn?
The integral is centered around 0.
What's the formula for bn? Do you remember?
I think it's the integral from negative, or 1 over 2L, the integral from negative L to L of f of x.
1 over L, not 1 over...
yeah, 1 over L from negative L to L of f of x times sine of, who was n omega.
Okay. Right? I'm helping, I'm working with you, so you're not alone. I have your back. So,
thank you.
So F, like John said, is even, very good. Let's say, Paul, you want to complete what John had started?
Oh, well, I was going to say the same thing. Because in the last class, we went over how if it was even, since it's from negative L to L, that the sign ends up being 0 when you integrate it.
What is even?
F of x.
You know, you need to show that bn equal to 0, right? F of x is even, yes. Then what?
Even function times an odd function.
Yeah, even function times odd function. What is odd?
Sine.
Sine function is odd, yes. So this is an even function times an odd function. What's the result? What's the integrand? Is this integrand odd or even?
It's even. That's right.
Odd.
Is that odd?
This integrand is odd. So odd times
Okay, I got that.
even is odd times even is odd. And so therefore the integral of an odd function that is centered
Both odd numbers.
over the interval is equal to 0. Okay. Now maybe that because there's some difficulty with this, perhaps let me propose a simple way to, a street fighting way to remember, just by picture. Okay, just by picture. So if you have, let's say, an even function, could be anything, need not be x squared, but as long as it's symmetric with respect to the y-axis. Let me do something like this. Yeah, that will be even. And let's say do an odd function. Perhaps one example would be something like this, something that looks like x cubed, right? That would be an odd function. So if you look at the area underneath the curve, right, and on this side here, okay, so the area in terms of absolute value are the same, right? It's just the sign. So this is, you can think of this as positive multiplied by negative, and here positive multiplied by positive. So therefore, on this side you would have the negative area, and on this side you have positive area. So therefore, the result would be an odd function. Okay. So that's one way to remember, just by picture, instead of the formal mathematics like I showed last time. Okay, and so now the rest would be to compute the coefficients for the cosine terms, right? And the constant. And I did mention to you that for the constant, there's a difference. For the constant, you have 1 over 2L, whereas for all other coefficients a sub n, from a1 to a infinity, the factor is 1 over L, and then we can show this. Okay. The rest, the integral is similar. If you replace n by 0, cosine of 0 is 1. Okay, so you have the integral of f. So here is the expression for the coefficient an and the coefficient a0. So a0 is the average, right? And since L is equal to 1, so this is, maybe let me ask the class here. Is it clear to you why this integral here is not from -1 to 1? Because the formula says that you need to, well, actually I explained over there. So all you need is just to explain, to explain the equality, right? The formula says that you need to integrate from -1 to 1. Okay, and multiply by 1 over 2L. But that is equal to this side here, which is 1 over L integral from 0 to +1 of fx dx y. Dylan?
It's just because L is equal to 1, you're saying?
Sorry?
Because L is 1.
L is 1, but I mean, how can you transform the integral from -1 to 1 to the integral from 0 to 1? I mean, how could the two sides be equal? There must be some explanation. Brandon?
The integral from -1 to 0 is equal to the integral from 0 to 1. So
Why? Why?
Because it's the same on both sides, except one's negative, so then we add
The function is
subtract one.
Yeah, the function is even. Okay, the function is even. So if you think in terms of geometry, the areas are the same. Maybe let's bring up this picture here. Right. If you look at, let's see, I can zoom in further here. Right. If you look at the integral from -1 to 0, like Brandon said, this is the area, whereas the integral from 0 to 1, that would be the area, and the two areas are equal. You can also prove analytically that this is the geometric intuition. So therefore, you can write what I wrote here is 2 times, right? If you take so the integral from -L to L of fx is 2 times the integral from 0 to L, but you have 1 over 2, so that's why 2 and 2 cancels, right? So that's the reason why a0 can be written as the integral from 0 to 1 of x squared dx, and that's the result there. And now the next step is to do similarly for this integral from an, right? And an is 1 over L, integral from minus L to L of fx cosine n omega x. But why? Why is it equal to 2 over L integral from 0 to L of this? What's the reason? Okay, I need to note down Brennan and let's see. Paul, John. Paul is team 3. John is team 4, right? Yes. And Brennan is team 3. Team 3. While I'm doing this, think about it and contribute, participate to get active learning credit. And then we have Dylan is what team number 6? 6. Okay.
Can you repeat the question?
Repeat the question. Okay. Explain the last equality. You know, why do you have this equality? Why can you write the left-hand side equal to the right-hand side? So we have Kyle, Paul, anyone else? So let's. Paul already taught, so let's start with Kyle, and then we have new fellow. We have Matt. What is your name? Black. Yes, Black. Need to put the name in. I know you contribute several times, so we have Matt. So let's start with Kyle. Okay, Black, Matt, and Paul. So Kyle, go ahead.
We discussed with the even function how it's going to be the same values on either side of the line.
So what is the function? What can you say about this product?
So you have the cosine, which is the even function, multiplied by f of x is an odd. So overall.
No, f of x is x squared. Okay.
Okay.
Yeah. So f of x is even or odd?
Even.
Even. And cosine is even or odd?
Even.
Even. So what is the product of f times cosine?
It's going to be even.
Even, right? So then.
And we discussed how any even function is going to be, it's the y-axis, it reflects on the y-axis, so it's going to be the same values.
Yeah.
So it's going to be exact same, for instance, exact same interval from 0 to L as it is from negative L to 0.
Okay. Blake,
No, it's
anything
the
to
same.
add to what Kyle said?
No.
No? You agree with Kyle? Okay. Paul? Okay. You already taught Paul, so let me ask Mark and then you can come next. Okay, Mark?
Yeah, so it's just the same thing, so you just multiply by 3.
So you agree with Kyle, right?
Yeah.
Yeah. Paul?
Yeah, since it's the same, you're just cutting the interval in half, so you have to multiply by a factor of 2.
It's not just because you've split this integral in half, but you need to say that because the integrand is even.
Well,
so
no,
therefore,
I'm saying what they said, it's even, it's the same on both
Right,
sides,
yeah.
but the interval is half as
right,
large,
yes,
so you
yes,
have to multiply
yes,
by 2.
yes, absolutely. Okay, so that's the reason. So let me just put down Matt here is team 8, and Kyle is team 6. Paul I already have, and then Black is team 3. Okay, so that's very good. So that's the formula, and what you need to do next is what I already showed to you in my in a previous lecture, right? And this is on successive integration by parts. You can do either apply the formula that I developed, or you can do integration by parts twice. And the trick is to determine which of the two factors is u prime, right? And which of the other factor would be v. Okay. So in this type of integral, which one you want to have v and which one you want to define as u prime? Remember, we went through this already. And it was, I asked this question already last time, and it was Casey who gave the correct answer. You just need to repeat what Casey said the other day. So which factor, because in doing integration by parts, you need to decide that it's a product of two functions, right? U prime and V. So which one would be more convenient to choose as U prime, and which one you want to choose as V? So we have Kenny G, not this time I remember, and wait a second. I know this is on the tip of my tongue, but look, Team 7, right? I'm sure it's Team 7. That should be Nick.
Yeah.
Okay, so let's start with Nick and then Ken.
I want to choose cosine because eventually cosine will be repeated in the integration, and you can actually cancel it out.
So which one you want to choose as V and which one you want to choose as U prime?
You want V to be cosine.
V to be cosine. How about Kenny?
I was going to say you want V to be x squared.
You want V to be x squared. And here's the reason. The reason is because you will, when you do integration by parts, you will differentiate V, right? Because U prime is already, if you choose this U prime and this is V, then you want to differentiate V, and up to a certain point, the differentiation of x squared would become 0. That's when you stop. Okay. If you choose the other way around, the integration may not stop because the derivative of cosines keeping it would not become 0, and that is in section 9D. And let me show you quickly for a quick review. It's right here. So basically, this is the application. Let me zoom in. Yeah. Right. Okay. Let's look at the first part. First, so you have the integral of x squared and cosine, and you want U prime to be cosine and V to be x squared, right? So the superscript in parentheses, it just means the degree of differentiation. So 1 in parentheses means U prime, and 0 in parentheses means V, okay? No derivative. And so that's the trick to keep in mind, because the first time you have V0, you have x squared. The second time you have V prime, and the third time you have V double prime. And that's stop the integration by parts. Okay. And the next example is similar, but just for sine. That's all. So that's the method, and that's it. With this, you can integrate all of the coefficients in the Fourier series. So now let me zoom out before I zoom back in again, so that you have the big picture. Right? You have A0 because all of the B coefficients are 0. Now you have a method to find AN to integrate, and this is the result here. And then you get the Fourier series, and has only cosine term. So let me zoom in to examine this Fourier series in closer detail. Okay. And now one thing that you want to note is that the expression for AN is in terms of n, right? And therefore you can put the Fourier series in compact series form with the summation. And this is very nice to code up in decimals, because then you can increase the number of terms to as many as you like. So I'd like to show you an animation that I created, and that's made available to all of you, and you can learn to code with Desmos using my examples, and I have also the manual of using Desmos posted in the portal that I had shown to you before. Okay, so now let me use the projector mode here, and so this is the let me zoom in. Right, so this is the original function that is defined as only one branch, right, of x squared between 0 and 1, okay, on a finite interval. And the goal is to extend this function into an even half period extension. So let me turn on this. Okay, so basically, yeah, maybe I should do this. I should okay, so first complete the parabola between -1 and 1, so into an even function, and then once you have this parabola, then I just translate. Okay, so this is just part of the let me zoom out here, part of the parabola in the negative side of x, and this is in the positive side, and one more. Okay, four times is good enough. So here is actually, it should be periodic from -infinity to +infinity, right? Okay. And now let's look at the average. Okay, this is the coefficient A0 here. So if you zoom in, you see that, let me zoom in over one period in the middle, then you see that this is the blue line here at 1/3. Okay, so 1 is from 0 to 1 there, and this is 1/3. And that's the average of the parabola. Okay, and down here, what I have is code for the Fourier series, exactly the same series that you saw in the in my lecture notes, in compact summation, and therefore I can increase m. M is the number of terms in the summation, and this is the slider that I have from 1 to 100. Okay, so I can have 100 terms in the series plus the average. Okay, so this is 1, m equal to 1. And let's see, oh, I need to turn on, yeah, so this is with m equal to 1. With m equal to 0, I don't have the 0, m equal to 1 is with one term. You already saw this cosine curve there. Let me zoom out. So you see that it's already started to approximate the periodic function. Except that here you have a king, okay? Keep this in mind. And now let's increase m to 2 or 3 here. And then continue to increase m. So now let me zoom in so that you can see the effect of increasing at the corner. When you look at this scale, it looks accurate, but if you keep zooming in, you see that it's not really, of course, you can never reach the peak. Okay, and so here is with 21 terms already. So now let's keep increasing to, let's say, you see, as you keep increasing, the Fourier series can approximate closer and closer to the king, but even with 100 terms, and if you zoom in, you still see that there's still an error. Okay, but that's pretty good. That's pretty good already. It's very accurate. If you look at the larger scale, and it's pretty sharp. If you zoom out, you see it looks almost identical to the original function. Okay. So that's Fourier series. Let's see. Let me turn off the approximation. So here, what you see here is the average, right? I have average at 1/3. And let me turn on only the summation, the second term here, the summation. Let me click here so you see. So the Fourier series has two parts, right? The average and the summation. Let me just plot this summation so that you can see the effect of the average and what it means by not having the average. So I turn on the summation here, okay? So that what you see here is, let me go back to m equal to 1, right? And what you see here would be the average, and the average is this horizontal line here, right? And the summation would be represented by this curve. Now let's increase the number of terms in the summation, right? You see? If I keep increasing until 100 or to infinity, you see that the second term alone can never approximate the exact function. That tells you the importance of the average term. If you miss the average term, your series is not good, okay? Because all it can do is just to give you this curve, which is far away from the exact curve. You need to add the average to bring it up, okay? So that's the lesson there. That's why I said in electrical engineering, the direct current component is very important. Okay, that's the average. Okay, so I think that should be good enough. Time really flies, so I'd like to stop this topic here and switch gear to music. Okay, in preparation for the Beatles topic, but I'd like to. So this is section 25E. Let me bring up section 25E. Let me close off all of these sections. 25E. Okay. So let me bring on two sides. Okay. So 25E, everyone sees here, and I'm going to skip a lot of things because I just want to focus on showing you two things. Basically, how to construct a spreadsheet that would represent the 12-tone equal temperament. Okay, so we don't have the full class today, but let me make a poll, and I do a poll again later, Monday or Wednesday. How many of you can read musical score? 1, 2, 3, 4, 5, 6, 7. Yeah, okay, 1/3 here. And so I presume that the rest of the class could not. But let's see. So those of you who can read musical score, I presume that you know what 12-tone equal temperament means. Okay. Now let me cut short the story, and I will come back to the story later, because it goes back to Pythagoras, 2,500 years ago. And even those of you who can read musical score, you may not know about music history, and you may learn something. Or if you know something, please participate and teach the class with me. Okay. But here I'll skip the story, and I'll come back later, because my goal is to help you to do problem 4.7. Okay. So let me show you the goal of the end result of problem 4.7. Let me skip here until that page right here. Okay. All I'm asking you to do is to create a spreadsheet with some formulas that I give you, okay? And I will zoom in. Because that's easier. So this is the spreadsheet. It contains the frequencies and then something else. So let me open up a middle window. I can close this one so I can zoom in. And so first I zoom out and go down so that you can see where I'm heading to right here. And now I zoom in, okay? Basically, the goal, and I will tell you the story about the famous Beatles song, A Hard Day's Night later, okay? So, but here the goal is the following. When you want to detect musical notes, you want to be able to, if you are given a frequency, find the notes, you know, in scientific notation, the musical note in scientific notation, right? For those of you who, let me show you here and then I will explain more later. For those of you who do not know about music, but everyone knows about the piano, right? So here is a short story. I have not a lot of time, so let me just show you on this side, or maybe on the other side better. I think I have a picture of a piano right here. Okay, and I will come back in more detail, but here it's just a preliminary explanation. The piano has 88 keys, okay, typical piano these days, 88 keys, and divided into a number of octaves. An octave contains 12 semitones, or a key, you know, including the white key and the black key. So if you, for example, here is a C. Okay, maybe I shouldn't get too deep into that. You just remember that there are 12 keys, black or white, okay? And it's periodic, by the way. We talk about periodic function, right? So this is also periodic. Okay, let me not going into the detail, but just if you focus on the first 12 semitones, okay? You see that the first key on the piano on the left is called key A0. And you go down, there are 12 semitones, meaning what is a semitone? A semitone is when you go from, let's say, key 1 to key 2, that's called an interval or a semitone. Okay, and if you keep going like that, then you have 12 intervals, and the name for each key, you have you go from A sharp, B, C, C sharp, D, D sharp, and so on and so forth. Okay, for example, here you do not have B sharp, and there's one more here, you do not have E sharp. Okay, so don't worry about why. We can talk about that later. But this is, you can think of this as a convention, of the naming convention, and over here is the octave number. Okay. Now the octave number, you can, so let's say in a not getting too deep into the details yet, it simply means that a higher octave corresponds to higher frequency. Okay. And it's periodic. Let me zoom out to show you. Perhaps let me use the this smaller window here, and going back down to this table so that you can see both parts of the table. Okay. So you see that in the first. Let's see. Oh, I have a jump here already because this is the first 12 semitone, and then I go to key number 49. You know, the piano key number 49 to key number 61. You see, it starts from key number 1. Key number 13 corresponds to the note A again, but at one octave above the other note A, and you can see over here. So you start with A0, and one octave above is A1. Okay, so that's why these numbers are called the octave number, and the note name goes from A to G sharp, and then back to A. because it's periodic. So this is also, a periodic phenomenon here. All right. So what's the goal? The goal of all this, okay, without just focus on the formula without explaining the detail. But at least let me say the following: to detect the musical notes, so meaning that if you hear only the sound, right, the song, and you record the song, you run the fast Fourier transform. Fast Fourier transform will give you the frequencies, okay? And given the frequency, you want to know what note, musical note, correspond to a given frequency, so that you can score on a music sheet, and then some artist or any other players can replay the song. That's really the goal. So, given let's say given a frequency, you want to detect that if the frequency is 1.25 hertz, that corresponds to the C sharp note of octave 1. Okay, so C sharp 1. That's the way you say, and it's called the scientific notation of musical notes. We'll get more into the detail, but here I just want to show you the formulas. All right, so what is the, this is the frequency factor. The frequency is right here. Okay, this is frequency, so this is in hertz here. And I will explain what the frequency factor soon. This is hertz, that's the frequency. Okay, so let me clear now the formula. Let me zoom out. The formula for actually the 12 tone 12 tone equal temperament is given here. Okay, this formula here. What it means is the following: given n is the piano key number. Let me put the mask on so to focus your attention. So let's say given n, which is the piano key number, and F1, which is the frequency for the leftmost key on the piano, that's the key called A0, right? And that frequency of that key is, of that note is 27.5 hertz. Okay, so this formula here will give you the frequency of key number n, which is equal to F1 times the 12 root of 2, meaning 2 to the power 1 over 12. Okay, so let me write down here. This is 2 to the power 1 over 12, and then take the power n minus 1. Okay, so that's the formula. And you'll see why it's 2 times 2 to the power 1 over 12 later. But let's accept this formula. This is the formula for the 12 tone equal temperament scale. That's a modern scale that is used in all musical instruments in modern time. And this key number 49 here is very important because it corresponds to what is called the pitch standard. The pitch standard is how the whole concert band is tuned. Okay, so it's tuned to 440 hertz. A4, it is the fourth octave, and it's also called A440. Now this 440 here means 440 hertz. Okay, so and that corresponds to the piano key number 49. So if you replace n by 49, and F1 is the frequency of the key or note A0, and you work out, you see that it's equal to 440, right? So the formula tells you that key number 49 on the piano has the frequency or the pitch at 440 hertz. Okay, so that's the meaning of this formula. Now, but you know, for music detection, for music note detection, we want to do the inverse. That means the following. That means that given a frequency, you want to find out what's the key number on the piano, right? So therefore, you want this to use this formula. Let me zoom in. Let me put on the mask. So what this formula says is the following: give Fn, meaning give any frequency, right? From fast Fourier transform, you would have a frequency. Find the piano key number n, right? So that's what this formula says. Now, because F1 is known as 27.5, that's fixed. Natural logarithm of 2 is fixed. Number 12 is fixed. So given Fn, you can find n. That's what this formula says. Okay. And the next step is the following. Okay. The next step, once you know the frequency Fn, but in general, Fn is not exactly that of a piano key. Okay, why? Because usually musical instruments, you know, you cannot tune perfectly. You have mistuning. And this procedure is very nice because it will tell you whether your piano is well tuned or not. You see, you can use mathematics to see whether your musical instrument is well tuned or not. And that is the following. If your piano is well tuned, if a key is well tuned, then n-1 is exactly an integer. But if it's not well tuned, if the key is not well tuned, then n-1 is not an integer, and you want to find the key number, the piano key number, that within an octave that is closest to the given frequency Fn. Okay? You will see the use of this more and more detail later, but let me just tell you the formula. The formula I found myself. This is not the same as in the paper by Brown. What I found is, I do this, okay, mod is a spreadsheet function that can compute the remainder, okay? So mod of m, 12 means the remainder of the number 12 divided by 12, right? And the round function is just rounding up, and here I round up to 0 decimal digit. All right, so let me see how much time. Okay, I think with this, I just want to go up and show to you two things before we quit, and that's here. You know, so frequency, given the frequency, you can find the number of keys. This is n here, basically n-1, and then the octave key number. So essentially, with these two formulas, you essentially can get these two columns. I'll come back in more detail on Monday. Okay. So please lecture summary and have a good weekend.